All right, so what we're going to talk about this unit is sort of a mixture of things. It's energy and temperature and exothermic, endothermic. And basically, the next three units are very important. And so this will just sort of be a transitional unit that'll cover some things and not be too difficult, as I promised you, because the next ones are going to be hard and the last one was hard. Anyway, all right. So when we talk about heat and energy and temperature, notice the temperature of these two blocks. This is an iron block and a brick block. They're the same. This is a FET that I will post if you want to play with it. And even though the temperature is the same, the energy in each isn't the same. And if we heat one up, let's say the iron, all right, and make the temperature higher than the brick, then that energy is going into the iron. And if we then put this iron on top of that brick, the energy will go from the hotter iron into the brick. Do you see that? It's also going to the less warm air as well. So some went to the brick, and then it stops when they're at the same temperature. In fact, if we link the heaters, you will see that even and we get them as full as possible, the brick cannot hold as much energy as the iron. So we'll be talking about that. So their temperatures are going up pretty consistently here, but there is a point when they reach the max that the iron can hold more of those energy blocks than the brick. And in fact, if we cool these things, it's energy that comes out that cools things down. We're not putting cold into anything. We're pulling energy out. So let's discuss that here for a minute. Basically, thermochemistry is what we're going to call this. And like if you've heard that there is no such thing as darkness, only the absence of light, there is no such thing as cold, only the absence of heat. So without energy, things are cold, but there is no such thing as cold. Energy is always moving around. And that's why we do the Kelvin temperature, and at 0 Kelvin, there's basically no more energy to move around. All right, so here we have some of those reactions like we talked about before, the exothermic, endothermic. If the activation energy to get to the activated complex is not that high, and there's a release of energy going from reactants to products, we say that is an exothermic reaction. We give it a negative value for its delta H being the enthalpy, basically the difference in energy between the products and the reactants. So if it's going down, it's negative. So releasing energy means you lose energy, right? So it's negative because the chemicals lost energy. Going the other way, it would be endothermic because now the activation energy is much higher. So going from here up to here would be the opposite of this. It would be plus 98 kilojoules to go up the hill. So endothermic reactions have a positive energy. So there's that little activation energy. It's like a bird. If it's jumping from a low branch to a high branch, it has to go over that branch and then come back down, right, to get to this activated complex. Likewise, if a bird is jumping from a higher branch to a lower branch, he hops a little bit. There's that little activation energy, and then he goes down. Anyway, that doesn't work. It's not that big a deal. So endothermic is the opposite of exothermic, right? It has to go up the hill for the reaction to occur. And at the end of the day, the chemicals have more energy because energy had to get put in. And so the delta H goes positive. So energy in is positive, energy out is negative. Okay? Now we can, with the use of a catalyst, actually reduce that activation energy. It doesn't change the distance between the products and the reactants. It just allows the reaction to happen a lot easier. So that's why I'm going to show you this thing here. Another FET. Yet another FET, Mr. Roach. Yes. All right. So here's the FET. And maybe if I make that bigger. So I have all my things here, right, at a higher energy than the product. And if I add some heat to this, they can move around a little more and they can get to a point where they can start jumping over that energy barrier to get to that activated complex and become a product. So the more energy I give them, the more able they are. This is taking longer than I anticipated. Here they go. So the more energy I give them, the more they are able to jump over that wall and get to the other side and become a product. There we go. Now we got a couple products. So what a catalyst is going to do is lower this so that more can get over there. Does that make sense? How now more are able to get over there because a catalyst has lowered the activation energy needed for them to get over. So that is what a catalyst does. Without a catalyst, this would be, back up here, and it'd be harder for the one product to be formed because the reactant is got to get that high thing, so lower and more go over there. And as you can see, there's sort of a sink of energy, or there should be, after this all comes to where it's there should always get to, well, we should get to a point where there's more red than green, because it's easier for them to stay down here in the lower right. The wall to get back is a little higher than the wall is to get over there. Anyway, all right, enough of that. So that'll come back and haunt us when we do acids bases. So how does how does the activated complex get lowered with a catalyst? What a catalyst will do is just line things up better. So here, if hydrogen is trying to react with chlorine to make hydrogen chloride, what a catalyst might do is just line them up so that they hit in the right orientation to become the products. If that makes sense, we'll get into that a little later. But anyway, definitions: heat is energy transferred between objects at different temperatures. Temperature, you may remember, is the average kinetic energy, how much things are moving, right? The symbol for heat is Q. Thank you, science. The symbol for temperature is T. We learned that with PV equals nRT. The units of measurement for heat is the joule or kilojoule. This used to be hard to teach 20 years ago. Thanks to modern science and technology, now people know what a joule is. Temperature is either degrees Celsius or Kelvin. You know this. To measure heat, you have to calculate it. Temperature, you read the thermometer. Okay, so heat and temperature are not the same thing. That's the point of this. Heat is a measure of the energy something has, hence joules. Temperature is just a measure of how fast things are moving, hence Kelvin. Okay, as you saw, heat flows in one direction, from the higher temperature thing to the lower temperature thing. And it keeps going until they reach equilibrium, basically when they reach the same temperature. The thing that gains heat, we've talked about, has that positive value. The thing that loses heat has a negative value, okay? So those are big picture things. There's this thing called specific heat. Specific heat is the amount of energy required to raise the temperature of 1 gram of substance 1 degree Celsius or 1 Kelvin. So the units of this would be joules per gram Kelvin or gram degree Celsius. So let's look into this. Basically, the kind of material affects how much heat they can have. If you look back at what we were doing with the iron and the brick, right? The iron was able to hold more energy than the brick. So the brick didn't take as much energy to heat up to a certain temperature as it took for the iron to get to that same temperature. And we're dealing with change in temperature. So here are some specific heats. You would never need to know these. They would always be given to you if necessary. But let's talk about why the world is so successful. We have a whole lot of water on this planet, and all that water has a very high specific heat, has a high mass, right? High density. So that water is able to absorb a lot of energy and keep the world temperate. And that's how room temperature and the ability for life to live at the temperature it has is possible. If you think about what a desert does, right? A desert gets very hot in the day and very cold at night because there is no water there to temper the heat. But when water's around, if you're by the shoreline or whatever, you have much more comfortable temperatures because that water's there to absorb all that heat. So let's look. Plastic, even though it has a very high specific heat, it's very light. You should know this, right? So because it's much lighter, it doesn't hold heat as well as something like copper, which has a slower specific heat than plastic. However, it's much more dense, so you can get a lot more mass in copper. So a large chunk of copper in the oven will burn your hand because it has a lot more energy to put into your hand than a large piece of plastic, which won't have as much mass to push that. So styrofoam, the same thing, right? Styrofoam has a very high specific heat, but getting enough mass of styrofoam to actually burn your hand is difficult. And that's what that's all about. Air, also a pretty high specific heat, but it's hard to get enough air to actually put energy into your hand that hurts. Okay, if you put your hand in an oven, the air temperature in that oven is as hot as the metal in the oven. But if you touch the air, it doesn't hurt because there's not as much mass of air to push that energy into your hand. Whereas the metal has a much higher mass, right? And therefore can push a lot more energy into your hand, even though it has a lower specific heat. So a high specific heat just means it takes pound for pound more energy to heat that up or cool it off. A low specific heat means pound for pound, it doesn't take as much energy But the problem is the pound for pound thing, right? A pound of gold and a pound of styrofoam weighs the same, but a pound of gold is a very small amount, whereas a pound of styrofoam would take up a large amount of space. Okay, so we talked about this, how Lavoisier put a hamster into an ice chamber and measured how much heat was released by the hamster by measuring how much liquid of the ice cage that he enclosed him in melted. And then from that measurement, he was able to determine how much heat was in the hamster. It's kind of a scary thing to think about, but they do this with people as well. If they have you exercise, they're not going to put you in that ice chamber. They're going to surround you with water, and how much that water changes temperature, right? So the room will be surrounded by this little water jacket, and that water jacket will increase in temperature based on how much heat you're releasing and how much that water gets heated up. They can then determine all came from you and how much heat was in you to start all that. So let's talk about this heating curve. Before we get into that, actually, let's look at this video. So I'm going to post this video as well. This is an interactive that I wished we could do, but basically what this is you put a substance here, and you're going to heat that substance up, and it's going to tell you what happens with the temperature. So there you see it's melting and the temperature is staying at 0. And then as the liquid heats up, it keeps getting hotter, and then it's going to stop heating up when it boils. All right. So boiling water, in this case, that's basically what they're trying to show you. Boiling water will stay at 100 degrees, and I'll show you another video of that, hopefully. So water freezing and melting happens at 0, and water boiling happens at 100. And it won't change even though you keep putting heat into it. So if you put a hot pot of water on the stove for an hour, it's still going to be 100 degrees. It's not going to get hotter than that. So here we're going to try the purple rock. And the purple rock, as the solid gets warmer, and then when it's melting, the temperature doesn't change. And then the liquid heats up, so the temperature goes up. And then when it starts boiling, it's going to plateau again. Okay, so we see here the energy for melting was all going into melting, so the temperature wasn't changing. And up here, the energy was all going into boiling. All right. So I will post this video. You can watch me discuss that because I'm hearing my voice in my background here. It's kind of frustrating, but basically what that means is there's a solid, and as you heat up the solid gets hotter and hotter, and you know this happens, right? Think about metal. If you put metal in the oven, it gets hotter than if it's in your house, right? So you can make a solid hotter without melting it, but it gets to a point where it melts. And when it melts, it does not change temperature. It stays flat. And then when it turns all to liquid, that's when it can start heating up again. And again, you know, there's cold water and hot water. Liquids can go up in temperature until the point where they're boiling. At the point of boiling, all the temperature stays the same because you're putting all your energy into turning that liquid into a gas. And then as a gas, you can start heating up the gas again. So that's called a heating curve. Here's another example of it where you have, this is specifically for water. You heat up ice to the point where it gets to 0 degrees, and then at 0 degrees it melts. If it's going this way, it freezes, and this way it melts. And then it all becomes water. That's when temperature can change again until it gets to a boiling point. And then when it gets to, everything has boiled into steam, then the gas can get hotter as you heat it up. Okay, but we can find the melting point and boiling point by finding these flat parts, and that's sort of the point that I'm trying to get to you. So at those flat parts, what you're doing is getting greater mobility, right? You're turning the solid phase into a liquid phase. You're trying to give more degrees of freedom to those atoms or molecules, and that takes energy. And it's not taking energy to make them move more, it's just giving them energy to break away from each other. Okay, and oops, going the wrong way. Likewise, when a liquid becomes a gas, you need energy to make those liquid particles break away, okay, from the attractive forces of the liquid. So there's an energy there, and if you try to bring them back in, energy has to be removed to get the attractive forces between these atoms or molecules back. So there's two things here. We call it delta H fusion and delta H vaporization. So the delta H fusion is deals with going back from solid liquid or liquid solid. That's the fusion. All right, the vape, again, liquid to gas. That's what vape is. So for water to turn from a solid to a liquid, so to melt ice to become a liquid, has a delta H fusion. It takes 334 joules, right? That's the energy per gram. It's an endothermic reaction. You have to put energy in to turn a solid into a liquid. It would be exothermic going the other way, so it would be minus 334 joules per gram going backwards. So that's the delta H fusion. The delta H vaporization is water liquid becoming water gas. You're putting energy in, so that's endothermic. Notice the bigger number, right? Takes a lot more energy to turn a liquid into gas. If you were turning gas back into a liquid, like what a steam burn is, when you have steam hit your arm and turn to a liquid, it releases that much energy. So it would be negative exothermic, and it would put all that energy into your arm or whatever it is you held over the steam to turn into a liquid. And we call that the delta H vaporization. So fusion is solid to liquid, liquid to solid. Vaporization, liquid to gas, gas to liquid. So which of these requires more energy, going liquid to gas or solid to liquid? As you can see, going liquid to gas is going to need more energy because gas is a really big freedom situation. All right. So at any curve like this, there's a change in temperature at 1, 3, and 5, right? Temperature can change of the solid down here, of the liquid up here, and of the gas up here. There's melting at that first flat part, and there's boiling at that second flat part. And if this is water, those are the representative energies associated with melting, fusion, and vaporization with boiling. All right, so think about this. When you put your ice tray into your freezer as liquid and it has to turn to gas, right? What happens next? It has to turn to solid. You need to pull out, for every gram of water, 334 joules to turn that liquid into a solid. All the heat that you're pulling out is what is released by your refrigerator. So if you've ever been near your refrigerator and felt heat coming out from under it, that's because to keep cold, right, it has to remove all that heat, and removing all that heat is what happens under the refrigerator. So if you had 480 grams, which is what an ice tray holds, of water at 0 degrees Celsius, and you just wanted to freeze that, how much energy do you have to pull out? How much energy has to be released by your freezer for that to happen? Well, there's 480 grams. The delta H fusion is 334 joules per gram. So it would be 160,000 joules need to come out of your water to make it turn from liquid to solid. All right, this is actually how sweat is supposed to work with delta H vaporization. Let's say you're exercising and you lose 500 grams of water. That water should be, if you live anywhere besides North Carolina, say you live in the desert or someplace where there's not as much humidity, that water actually leaves your body and evaporates. And when it evaporates, it takes with it this delta H vaporization, right? So 500 grams of water sweating, every gram will give you 2,260 joules per gram. So that's how many joules your body should be releasing, how many energy blocks your body should be releasing when it sweats. Now, the problem why, like I said, here in North Carolina, this water doesn't go anywhere. It leaves your body and just stays on your skin because of the humidity, so you don't feel this benefit. But if you've ever been someplace that's less humid and where you get sweating, you actually will cool off if you sweat, because that evaporating water will cool you off by this many joules and take all that energy away. So that's how sweat was meant to work. It just doesn't work in North Carolina. All right, so the other diagram I want you to know is this thing called a phase diagram. We kind of hit on this a little already. The phase diagram pits temperature versus pressure. Now, this is different from the other diagram, which pits heat, basically. Not heavy, right? So heat energy, so you're increasing your heat as you go here, versus temperature. So it's similar, but it's not the same. We're doing pressure versus temperature here for this phase diagram. So temperature versus pressure. And hopefully you would know at low temperatures, solid, liquid, or gas, what do you think you're going to have? You should think that that's going to be solid, right? So this area of the graph, this whole area here is solid. The area at high temperatures, right, when you have a lot of energy for those molecules to move around, low pressure, so they're not very close together. This is the gas phase. So this whole area of the graph is gas. And then in between solid and gas, guess what you have? You have liquid. So this is the part of the graph that we would call liquid. So I would need you to be able to identify those three things. If we look at this a little closer, this is the phase diagram for water. So at 1 atmosphere pressure, so basically the pressure on Earth, you have a solid turning to a liquid at 0 degrees and a liquid turning to a gas at 100 degrees. And remember, when I decreased the pressure, right, I took the water and I put it into that little jar and put it onto a vacuum. I decreased the temperature it needed to boil, right? Instead of boiling at 100 degrees, it was boiling at room temperature. So that is how I did that, using this graph, basically. So decreasing your pressure to something lower, let's say 0.3, then I lowered the boiling point of water. Okay, and then there's this thing here called the triple point, which is where all three phases, solid, liquid, and gas, all exist. Think about it. If you ever had one of those places where you can stand in 3 states at the same time, that's basically what the triple point is. This thing up here is called the critical point, which is just a point where you can't be anything but a gas anymore. There's some other things there. All right, so remember, boiling's definition is when air pressure equals vapor pressure. And if we took air pressure away, then it's easier for things to boil. All right, so here's carbon dioxide, dry ice. I'll post a video where I show you the triple point of dry ice. I can achieve that in a syringe. But the same general pattern here: solid, low temperatures; gas, higher temperatures; liquid in between those two. Triple point is where everything comes together, and the critical point's up there. So I've posted a video where I show you the triple point. I show you what liquid carbon dioxide looks like in the presence of gas and solid carbon dioxide all together. But I needed to increase the pressure. So I put it in a syringe and put my finger over the syringe to build up the pressure. And so ballpark, when you see that happen, it's about minus 56 degrees Celsius in the syringe. All right, last kind of thing I want you to know. And again, I told you this is a bit of a mishmash, but you throw salt on those roads when the snow's coming, right? And why does that lower the freezing point of the water? Well, the reason is if water as a liquid, so here's liquid, wants to become a solid, it needs to be nice and ordered, right, for this to become a solid. And if you throw some impurities in here, these salt particles in here, it's going to be harder for that water to become a solid because it can't line up perfectly anymore. It's this irregular shape now, and because of that, you need a lower temperature to get this to be a solid. And so when you throw salt in water, water won't freeze at the same temperature. So this is 0 degrees Celsius. This is going to be lower. This could be like minus 10 degrees Celsius, because now you have to slow down the particles even more to get them to be a solid, because now they have these little impurities sticking there, getting in the way of things. So that's why we salt roads. It will reduce the freezing point of the water. And then if you put salt into water, and this is actually why I went to graduate school, because I had this question, I didn't quite understand it until after I went to graduate school. So if you put salt in water, think about that. Here's a salt particle, right? And salt doesn't boil. So if you're trying to boil water, you have two problems. You have these salt particles pulling the water toward them, right? Because of their positive, negative thing. And also you have these things that don't want to go anywhere. They don't want to leave. And so they're blocking any water that wants to leave. So in order for water to boil, it now has to overcome a new thing. It has to overcome the fact that these particles are in their way and any attractive forces these particles have. So it raises the boiling point to put salt into water, believe it or not. And I'll do a video where I show you that. And with water freezing, it lowers the freezing point. So it kind of goes both ways. What it does is it makes the liquid to gas phase go this way, right? So this is with salt. And it makes the solid to liquid phase go this way. So it lowers the freezing point and increases the boiling point when you add salt to things. All right, I was going to talk about how that works. I guess that's it. So you can stop listening now if you don't care how air conditioning works. But how air conditioning works is in the house, it's turning from a liquid to a gas. And for a liquid to turn to a gas requires energy. So that's endothermic. Endothermic. Don't ask me why that just happened. Endothermic. So it needs energy to turn from a liquid to a gas. So energy comes from the house. Little energy blocks have to come from the house to heat that liquid up to a gas. And then they compress that back to a liquid, okay, in the compressor. And here a liquid is, or I'm sorry, a gas is going to become a liquid. And in the process of that, that's now exothermic. It releases heat. So that's releasing heat. And outside your house by that fan, all the heat comes out. All that energy blocks start coming out at this point. So all the energy blocks from your house went into turning that liquid into a gas, boiling that liquid that's in your uh, coolant. And then when it came outside, all that gas went back to being a liquid and released that energy outside the house. Inside the house, the energy went into the liquid becoming a gas. Outside the house, the energy is released when the gas becomes back into turning into a liquid. And that's sort of the cycle that happens with air conditioning. All right, there it is. Much too long, but hopefully you can deal with this. And like I said, I promise no math.